All right, good afternoon. Thank you everyone who's made the time to be with us this afternoon for the webinar. We really appreciate it. My name is Alex Canny and I'm with ACS, Division of Preferred Utilities. Been with Preferred Utilities and ACS for about 10 years, and my background specializing in fuel systems for backup power generators, do boiler rooms as well, but really focusing in on the life safety and mission critical applications for backup power fuel systems. And we also have joining us Brent Geis.
Hey everyone, it's Brent Geis. I've been with Preferred for about 25 years, doing everything from service to design to sales to anything you need, Preferred Utilities related. Look forward to doing this with you guys today and going over what we have to present.
Excellent. All right. Just give a brief rundown. We got some introductions here at the beginning. We're going to introduce the company as well. I know a lot of you are probably already familiar with Preferred Utilities. Maybe have joined us for a lunch and learn or a webinar in the past. And then the three basic areas we're going to be looking at today when it comes to fuel compatibility for mission critical systems. They're going to be the materials as it relates to low melting point. It's going to be material and chemical interactions with the fuel itself. And then finally, we're going to do a section on the physical construction, looking at the tanks, the piping, the valves, how the placement and physical construction of those can affect fuel quality, and really throughout how fuel quality and system performance is related to these material selections and chemical interactions, and how they're kind of, they both rely on each other. The fuel quality keeps the system running properly, and the system running properly keeps the fuel where it needs to be as far as quality. Now, I do have closing questions at the end, but we really encourage, if you can, if you're on the chat feature there, feel free to drop in questions anytime. We will get to the bulk of those at the end, but don't wait to the end to ask the question. If you have the option to ask that now, go right ahead, and we'll see those as they come in. All right, so jumping into the introduction for Preferred Utilities. Been operating continuously since 1920. A lot of engineering experience. We're a very engineering heavy company for a manufacturer. Headquarters in Danbury, Connecticut. And as I mentioned before, mission critical facilities is really where we tend to focus. We do a lot of different projects for higher ed and production facilities and things like that. But when we're talking about some of these topics like fuel oil, a lot of it's going to come down to healthcare and other facilities along those lines. We have offices across the country and representation as well in addition to those offices. And today we're going to be talking about mostly fuel oil handling, but we also have our major divisions that include boiler controls, combustion systems, and even nuclear outage support. So if there's anything along those lines that we can help you with, don't hesitate to reach out via the web or give us a call. All right, starting off with our first subtopic here, melting point. So one of the things I like to do, if you've ever seen a seminar or a webinar that I've done in the past, is before we jump right into the first topic, I like to take a second to talk about centralized fuel systems, because some of the folks that may be joining us may not be familiar with some of the terminology that we're using, or even just the layout that we're referencing when we're talking about some of these topics. So I like to start out with a overall system diagram that is representative of what we're going to be referencing throughout the presentation. Over on the lower left-hand side there, you can see in this case we have a buried or vaulted bulk fuel storage tank. Most of the fuel is going to be stored there. That's where it's going to be delivered. In this case, we're showing one where it has an in-ground fill container. That fuel is then pulled out of the tank via the duplex transfer pump set in the center. And that is where traditionally the bulk of the controls were located. Some modern systems have more peer-to-peer controls, but traditionally they were mostly located at the transfer fuel skid. And then off to the right-hand side, we have a fuel polishing skid. We're going to talk about that more as we go on in the presentation. And then up top, we have the point of use of the fuel, in this case, an emergency generator pulling off of a standalone day tank. So as we go through the presentation, we're going to be talking about a lot of valves. We're talking about tanks, piping. This is really what we're referring to in many cases. And A lot of modern systems can take the form of just a direct fill belly tank, maybe under a generator out on a lawn at a facility, depending on where you are in the country, right? If you're out on the West Coast, you may have a tank up on a roof that's direct fill, and so it won't quite look like this. But here in the Northeast, a lot of what we're dealing with are more of a traditional, what I would call a centralized fuel system, where the bulk of the fuel is being stored in one area, whether it's inside or outside the building envelope, and then there are transfer pumps to move it to day tanks or sub-base tanks at the point of use, and then we have a standalone filtration unit here. Brent, is this typically what you would see down in your area as well, in the Maryland area?
Yeah, for the most part, Alex, it's very similar. We have vaulted designs. I'd say there's fewer of those, but they are starting to come around a lot more recently, and we're being asked to provide vapor detection systems in those vaulted areas. That's something else that we can combine with our packages. But for the most part, we see above ground and underground storage tanks, duplex pump skid feeding one or a number of generators or boilers. And every one of them, we try to support filtration. Filtration is critical in this area, especially with how humid the environment is, which we'll get into later on.
Absolutely. Um, and then, so jumping right into our first topic here, low melting point materials. As you mentioned, Brent, things are different in different areas, right? Whether it's different jurisdictions, different climate. And this topic especially is going to be very regional. Not only regional, but also maybe by the insurance carrier that someone has at their facility. So there are some jurisdictions and some insurance carriers that are trying to get away from copper alloys or other low melting point materials. And the thought there is that failure during a fire maybe could introduce more fuel to the building envelope or to the area that is impacted by the fire, or causing just a general spill. And I think this is something that it's hard to make any sort of a general recommendation across the country, as is the case for many aspects of the fuel system. It's important to work with the local fire department and to work with the insurance carrier to find out what their specific requirements are. It's not always the case that systems that have these materials are necessarily unsafe. I think a lot of systems have been designed this way for a long time. But the specifics really matter. And one of the things here, it may also include non-ductile materials such as cast iron. So it's not a one size fits all rule in this case. And as far as code, the International Fire Code does reference it under the special materials section, but it references it talking about it needs to be suitably protected, right? So if it's going to be exposed to fire, obviously when it's a requirement that is that general in its language, it can be interpreted in many ways, and that's one of the things that we see a lot of. I'm located here in New Hampshire, and we see a lot of differences state to state, fire department to fire department, on how they're in interpreting the language in the code. OSHA echoes kind of the same language as the IFC, and then the NFPA really doesn't get that specific. It talks about compatible materials, but again, it may be something that is more driven by insurance than it is necessarily code. Brent, what are your thoughts on this? What are you seeing down where you are?
So there's a lot going on with what's considered low melting point materials. The first thing is just soft material, and that is driven by your older systems in schools. We see it a lot in the older schools that fire oil, uh, primarily in rural areas that never really had natural gas delivered to them. A lot of the underground piping is copper, and it's still copper. And that presents an issue over time. Not that the copper is degrading, but it is a soft metal, so it's collapsing. It's giving them some trouble, and all of that's being replaced by black iron pipe or just standard piping in general. uh, Low melt point materials in, say, Maryland or DC, their codes, local COMAR requirements, have opted to go in a direction where they are very particular. They want to see no low melt point copper type uh, additives in the systems. That includes maybe anti-siphon valves, bronze valves, brass ball valves. They can be very stringent. Now, I'd like to say it's also based on a very local aspect, meaning that a fire marshal may be fine with what you're supplying because you've mitigated the risk for fuel spills or fire prevention, or you've got tanks that are way out in a field somewhere that aren't going to do any type of damage to a local building or whatever it may be. However, then Maryland also has their Department of Environment that you have to take into consideration, and they are looking for material that may leak over time, and that's where they fall into low melt point materials. Overall, specifically in Maryland, Department of Environment is the overseeing agency of these systems. Now, if you take a step into Washington, D.C., with inside their city limits, they require all systems to be without low melt point materials. No room for error at all. And they've actually gone so far as to start putting out a lot of projects in their plumbing code that require those current devices that are brass or bronze, copper, to be removed and replaced in kind with something that is more durable, steel, stainless steel, etc. So a lot of those codes are interpretive. NFPA 30, for instance, actually mentions low melt point materials, but it allows you to not necessarily have to use them if you have mitigated the flow of fuel in a fire event. Give you for instance, you can install a uh, Fusomatic fire protection valve on a main tank that is steel, and then everything that's downstream of it, we have seen the ability to use other materials, common materials that have been used in fuel oil for history, bronze, brass, etc. Uh, like I said, it's very conditional. It's has a lot to do with the local jurisdictions and what they are comfortable with. I've also seen insurance carriers, specifically FM Global, go around and actually test valves and things like that with magnets. So it's there is a gray area, but we are beginning to see extremes one way or the other. Either they're for it or they're against it. It doesn't matter. We're just presenting the information. And when a project is being designed, uh, do a little homework, speak with the fire agency, and make sure that you're going to be covered for your complete design.
Absolutely. So it sounds like ultimately we have environmental authorities that are local to a project they're concerned about a spill, and we have the fire authority, with fire inspector, fire department. They're worried about mitigating that issue, and then the insurance company is working on risk management. So those are kind of the three things that we have to be worried about, no matter where we are in the country, I would say.
Absolutely. Anywhere in the country and for a variety of different things, totally outside of anything to do with the actual material itself.
Right. And we see, I'll say up here in the Northeast, I did quite a bit of work in Vermont in the past, and even here in New Hampshire and Maine, and we still see a lot of legacy systems that have copper piping or tubing, I should say,
Absolutely.
copper tubing.
Yeah.
And yeah, I will say that's posed a lot of challenges for several reasons on jobs. So seeing that go away as a basis of design definitely will be a good thing going forward.
Yeah. Even our pipe sizing programs and things still offer that as an option because they are still around.
Right. All right. Let's get into our next subtopic here: chemical interactions. Um, this one it covers quite a bit, right? We're talking about any sort of chemical interaction that can affect fuel and the different types that we're going to be talking about. So when we're storing, transferring, handling, what does it come in contact with? So it comes in contact with two basic categories, right? The materials, like tanks, piping, and valves, and then it's always in contact with the chemicals in the fuel itself, right? So the fuel isn't just one static thing. There's additives, entrained water, all kinds of contaminants, right? There's a lot going on in those tanks, and all of that can affect the fuel and affect the performance of the system. And it's important to be aware of what those things are. So diesel fuel, it's an organic product, right? And it does have a shelf life. It has a better shelf life than some other things like gasoline, which is one of the reasons why we use them for systems that we do. But it does begin to decay as soon as it's refined. And any system that is active and not completely sealed up and mothballed is going to get water entrainment. There's air exchange. There's moisture in the air, and so you're going to have different things that you have to address. One of those is sludge formation, right? So it's an organic process, and one of many things that's made worse by the presence of water, because the bacteria and fungus, they actually live in the water and then feed on the fuel, and that generates the sludge that can clog the system. Brent, you mentioned down where you are humidity, and I think up here in New England, if we have coastal areas or other places, we can definitely see some are impacted more than others, but I would say in my experience, almost every tank has some water in it. What's your experience with water entrainment?
So a lot of times it depends on how much fuel you are maintaining in the tank in which the fuel and the air as you get moisture in. Okay, I'll give you for instance, if you have a 300,000 gallon tank underground, or even a 10,000 gallon tank above ground, and they are only a third full, quarter full, you
Mhm.
have a lot of area for water to condense on those sidewalls. So I've seen everything from virtually no water in a tank that is maintained and kept clean to gallons of water in a tank, and they all present challenges. So I know we're going to get into a filtering fuel and some other things, which we can, but humidity is a big deal. It's coming in as you are expelling oil from the tank and using that oil. You have now surface area inside of a tank that will accumulate water, and water will sink down to the bottom of the tank and start building bacteria, fungus, and creating sludge. And that is one of the number one reasons for generator systems and boiler systems to no longer operate is sludge, which we want to avoid.
Absolutely. Yeah, it's not just the fact that the water, it's not water getting into, generally speaking, the generator inlet itself. Especially with a centralized system, it'll drop out in the main tank and the day tank, but it's all those secondary effects, right? And one of the things I'd like to touch on here while we're kind of getting into this part of the topic is we're by and large referring to diesel here, right? And one of the things that we're seeing it's a big trend, and it's something that we can certainly help folks out with as well, although it's not a main topic here in this presentation, is biofuel. And one of the things that I've run into in doing biofuel projects and researching biofuel is that generally speaking, it likes water even more than diesel, and not in a good way. So the old adage, oil and water don't mix, right? While partially true, when you have traditional petroleum products, right, you tend to get that separation, and we're going to talk about that a little more later. But when you're talking about biofuels, depending on the blend and depending on the feedstock, you can actually get a fuel that's more hydrophilic. And the problem with that is not just how much it mixes with the water, but also how much it's actually pulling the moisture out of the air. And so I think this is an issue that is going to actually become more significant when we see more and more biofuel projects. Have you seen those type of projects come up in your territory, Brent?
We don't have too many biofuels down here. Most of the systems are either gas and or oil, period. Because they fuel the primary fuel for all the boiler plants, for instance, is strictly natural gas. And then number two, fuel oil has a more stable shelf life than your RFOs, your bros, and your biofuels. Therefore, they're only using the fuel oil in the event that they lose natural gas as their primary source. So therefore, that fuel would be sitting for a long period of time. And
Mm.
although important to clean for diesel fuel, even more important for your biofuels. So you don't see too many of them down here in this area.
Okay, yeah, we're seeing that crop up quite a bit here in New England, but it could be one of those things that kind of spreads regionally. Um, so we're talking about water and sludge. One of the things that's important is something I touched on at the very beginning, and that's kind of the symbiosis here between fuel quality and tank quality. So you have different forms of corrosion. In this case, we're talking about the corrosion that can occur when you have sludge production. One of the byproducts of that is that can be acidic. And when you have this sort of sludge production happening at maybe the surface of the tank, it's interacting with the bare metal. You can have some pitting and other types of corrosion happening within the tank that then turns around and kind of feeds that same cycle. And so you have that with steel tanks. You can also have issues with fiberglass tanks. We're going to talk about that in a little bit as well. So, you know, these all of these chemical and material interactions that are happening, they kind of feed off of each other. So it's important to know what's in the tank, what kind of contaminants are in there. Is it water? Taking care of these issues preemptively. And we're talking about liquid water and the fuel. I know a lot of people are very familiar with this topic, but for some maybe who aren't as familiar, so typically your water is going to collect at the bottom of the fuel tank, right? And your sludge production, as we mentioned before, kind of relies on water and fuel. So it's going to be at um, that line there between the water and the fuel where the sludge is going to be produced. And the reason that that's significant is if we take a look at um, the next slide here, where we're showing some very well mixed water and fuel and probably other contaminants. The problem with this is when you have a system that has water not just at the bottom of the main tank, but you have it throughout the system, the sludge production can be exponentially higher, not just because it's happening throughout the system, but also that water is forming small globules and the surface area is exponentially larger than it would have been if it had just been at the bottom of the tank. So one of the things that we see people doing, and it's not necessarily wrong inherently, but they'll do things like circulate the fuel or put in some additives to disperse the water. And if all the fuel is going to be used in a short amount of time, like say, you're putting dry gas in your car and you're going to burn through that tank of gas in a week, that's one thing. But when we have facilities that are using fuel on longer and longer time scales, that can actually backfire and it can actually cause sludge growth throughout the system at higher rates. I've even seen systems where piping and valves had to be removed and either cleaned or replaced because there was so much sludge growing throughout the system, not just at the bottom of the main tank. Brent, I know you're somewhat familiar with the fuel that we're looking at here. What has been your experience on that?
So yeah, that picture I actually took probably over 10 years ago. I was working in a boiler plant that we were having a hard time lighting off the burners in an urgent emergency condition on fuel oil, and we could not light the fuel. Well, come to find out after taking a test in this cup here, that's not pineapple juice. That is the water that had accumulated in the tank, and the water had gotten so high that the fuel oil pump drop tubes were just pulling straight water, no mixture of fuel oil whatsoever. We ended up pretty much draining several hundred gallons of water out into 55-gallon drums
Mm.
at this facility before we were able to establish oil flow. And then once we did begin flowing oil, we had issues with clogging strainers. Um, One thing you don't think of is like burners. Burners or even generator injectors, like very fine holes for atomization. And when you get such fine holes, they can plug up, just like your car fuel injection system can plug up. And we had a lot of issues with that to get this particular project moving forward and giving them the ability to fire their boilers in a emergency no gas type situation. But overall, a couple things to look at if you are trying to fire burners and you're one of the burner guys out there. Take a look in your sight glass in the back. If you see a lot of sparklers, which look just like little sparks firing from your furnace or from the main flame, that's water. That's water intrusion that's burning off that you're seeing. So that's a good indicator that you really need to do something with your fuel oil.
Absolutely. Absolutely. So, I mean, as far as contaminants, I mean, we have things like filters to pull out. If we have grit in the system, I think one of the worst ones I've seen is metal filings or welding slag. I know that can be an issue on startup, especially if you have a lot of magnetic operated things like that. But overall, I think by total amount of headache, water is probably the biggest one. And there's different ways to determine the quality of the fuel. You can have samples sent out to a laboratory. One of the things to look for there is where you're sampling the fuel. Some people take samples at different depths in the main tank, or maybe taking a sample from the strainer and the pump set to see what's being sent up to the day tank. And keeping an eye on the fuel. A visual check is never a bad thing, as we saw on the last slide there. And even looking at parameters such as a high suction vacuum on a transfer pump, gives you an indication on viscosity or other contaminants that are in there. NFPA 110 makes some recommendations. Brent, you touched on this a little bit before, but keeping the tanks as full as possible. Water entry through the headspace. When you have one of the things that we see here in the Northeast are places where they would have been primarily on liquid fuel for, say, a boiler plant with some additional storage for the generator backup power system. And then we have, they've migrated to gas firing primarily, right, during the heating season. And so they have very large storage tanks, compared to what they would have if the plant had been built around just gas primary, right?
Yep.
And so we have a couple of options, right? They say, well, we can either keep 20,000 gallons of fuel on hand and burn it over the next 15 years or 20 years, because just so much fuel, and let it age, or let's just fill the tank halfway, right? And that's I can understand it can be kind of a hard decision, but the impact of that second decision is definitely significant, as you mentioned with the water entry. And one of the things that we was really unexpected here in the Northeast, because best practice has changed a bit with how the vent lines are done. Historically, on large fuel tanks, you'd have a small operating vent, maybe 2-inch, going outside the building, right, to allow the tank to breathe, and then you'd have E-vents that were mounted directly on the tank, either weighted or sprung within the building envelope. And one of the things that we've noticed is with the jurisdictions that have gone to remote emergency vents, because those tend to be much larger, even on a day tank, they can be 4, 5, 6 inches, and on large tanks, they're quite large. By requirement to be able to vent those tanks in an emergency, we're seeing even more water entrainment. And the way that we actually started noticing that was on the interstitial, because there's typically a separate event for the primary and the secondary on double wall tanks, and we were getting all kinds of water alarms on the interstitial, and it was from those larger lines being run outside the building. We're now seeing those temperature inversions affecting the air in those lines as well. So it seems like no matter how you set up your tank, you're going to get water entry somehow, but when we increase that headspace, it definitely seems to make that much worse. So what are some of the things you can do? Well, I mean, obviously, an underground tank may have an advantage on thermal cycling, right? But really what you want to do ultimately is find a way to remove it, because at least in my opinion, in my experience, it's going to find a way into the tank. One of the ways you can do that is with a standalone filtration unit. And there are companies that will come in and they do a great job. I've seen it myself, where they'll come in with a temporary filtration unit, and they'll go ahead and filter in place. and you can have them in, once a year or something like that. But if we're talking at the design phase, like if we're designing a new fuel storage system, uh, we really can't influence what the person's going to do, years down the road. But having something like this in place and ready to go, and most importantly, when we're talking about this filtration, not just the filter, right? Not just the ability to recirculate and filter the fuel, but the ability to remove that water, and separating it from being mixed in with the fuel. And on this slide, we just have an example of what typically to look for within a filtration unit. And it's important to understand that on the first slide that we showed, it's a separate unit from the transfer pump set, right? We get requests, or at least I get requests all the time for a combined filtration and transfer pump set. And although, in theory, it's not a bad idea, one of the things we want to be able to do is separate a lot of these single points of failure from actually transferring the fuel to the generator. So it typically should be standalone, and it should be on its own piping loop as well. We want the drop tube for this filtration unit to go right down to the bottom of the tank and pick up that water and sludge and everything that sits down there. And we don't necessarily want to send that up to the day tank with the transfer pumps. So, Brent, what has been your experience in with filtration units? You see a lot of facilities adopt these now. You said it's pretty much a requirement almost.
Yeah, I mean, just about every specification that we do, or anytime we speak with end users, that one of their number one complaints is fuel quality, especially with how much fuel costs nowadays. They want to make sure that that they can keep it as long as possible and use it and have it accessible when they need it. So filtration has become almost a standard. Now, a couple key notes that I would point out is there are a ton of manufacturers out there. Most of them use the exact same filter and filter canister that you see in this picture, actually, for the smaller units. But there's few manufacturers out there who actually have different filters or filter designs. It's fairly common that they all use the same. Now, that being said, there's a lot of specs out there that may say, hey, I can do 7 stages of filtration and I can do 25 stages of filtration. That's awesome. That's great. Those systems cost a lot of money, and the end result is you're still getting down to 5 or 2 or 1 micron filtration um, that every system has the ability to do just by a filter cartridge. That being said, keep in mind that generators and generator filters are usually a 10 to 20 micron filter that feeds their generator. So anything below 10 or 20 microns is perfectly acceptable and going to work really well for your system. I would never recommend going below 5 micron. The facilities that have opted to go 1 or 2 micron filtration tend to have to change their filters a lot more frequently, and with an expense of changing those filters. And there's really no reason to.
Right.
1 micron, 5 micron, can you tell the difference? It's not going to make any difference to any of the equipment out there, boilers or generators at all. So
Right.
just keep those things in mind.
Yeah, I mean, unless we're talking some ultra rare, turbine application or something like that, right? I mean, yeah, we definitely don't need to go smaller than the actual filters on the generator. That's a really good point. One of the things I tend to look for, and one of the big differentiators when I'm doing a startup on a job or something like that, is just physical size. If I have a 10,000 gallon tank, but I have a quote unquote filter or polishing unit that's the size of a briefcase, it kind of gets me thinking, how much water could that unit actually pull out if there's, 0.5% of water in that fuel or something like that? Or, what's the pressure drop across that filter? I think sometimes, it's rated for a certain amount of fuel, but really that comes down to a lot of different factors, right? Runtime, filter size, things like that. So, you want to make sure that we're actually being realistic with that equipment.
Yep.
All right, one last slide on chemical compatibility, and this is really just to kind of get people thinking more than anything. And it's to really to get you thinking about, okay, what else is in the fuel, and what else is in my tank. There are fuel additives, right? We know about ethanol. There are varying levels of sulfur. What about additives in the future? When we're talking about fiberglass tanks or composite tanks, right? The resin is not as inert as maybe we'd like to think, right? So there can be just as many challenges as you would with a bare steel tank, delamination, blistering, cracking, all the sorts of things, and the resin recipes change over time. Copper alloys, right? When we're talking about biofuels, some of the studies that are coming out show there's a higher corrosion potential with biofuels. Not even, talking about the water entrainment. So these are just things to think about. It's just not quite as simple, straightforward, and cut and dried as we would like. There's a lot going on chemically inside these systems, and we really encourage you, if you have a specific application, to reach out to us on that, and let's talk through it. Let's find the areas of low-hanging fruit where we can, make the most impact on that system. All right, final section: physical construction. So, well, why does the tank design matter, right? Isn't it all the same? Isn't a square tank going to be the same as a round tank? Is going to be the same as a small tank? Is going to be the same as a big tank? Well, not always. And keeping with the theme of that symbiotic relationship, right? The fuel health is directly tied to the tank health. If you have a rectangular tank outside, and I noticed the ones that seem most susceptible to this are the ones where the height is just above eye level, and it's growing a forest of moss up there, and water's sitting for extended periods of time, that tank health eventually is going to be impacting your fuel health, right? So if it corrodes or is punctured, the fuel is going to be affected, even if you're double wall eventually. And the other thing is we can control the design, placement, and construction of the tank at the design phase, right? So we can't always control what people are going to do for maintenance and checking later on, but we can take steps on the design phase if we have that opportunity to impact that. The basic materials of construction that you're going to run into in terms of frequency, I would say, would be carbon steel. Second being fiberglass, which is going to be almost exclusively underground tanks, and then concrete. And those are not quite as common. We see those sometimes with like fueling systems for fleets, where they'll have like a rectangular concrete clad tank out in a parking lot maybe. And to be honest, we've had a lot of issues there with that style here in New England, just because it tends to get micro cracks between winter and summer. So really the two big ones we see here in the Northeast are carbon steel and fiberglass. Brent, what are you seeing down where you are?
Yeah, I don't have any concrete unless it's a UL 2085 tank. And of course, you have the inner carbon steel wall, outer carbon steel wall, and then a portion of the interstitial spaces between the two is the lightweight concrete to give it the UL 2085 fireproof rating or a ballistics rating, depending on where you're located. So, yeah, pretty much carbon steel and fiberglass down here. You know, uh, uh, when I think it was during COVID, Alex, we had talked, and I think there were a few that were um, uh, fiberglass clad steel tanks that were going in underground. Was that correct?
I have a slide on that a little bit later. Yeah, it's kind of one of the hybrids that's an option to keep in mind. So yeah, we'll definitely talk about that.
Yeah, but
Uh,
we don't see them too much, not too much anymore. And for the steel ones underground, we definitely don't see underground steel tanks. The existing ones that are there at times can be clad uh, and retained, but it's almost as expensive as just putting in a new tank.
right, right, absolutely. Um, Taking a look at some of the options here, again, these are general comparisons. It's going to vary by where you're located and what you have available to you, but carbon steel, we do still see this in the Northeast underground or above ground. It has good fuel compatibility, but cathodic protection was something that historically I think was a really big issue. Or having that cladding if it's going below ground. We do you see a slightly smaller footprint than the fiberglass, just because the fiberglass tends to have those large ribs around the side for reinforcement. On the fiberglass side, they do tend to be lighter for transportation. One of the things we mentioned before, it's important to keep an eye on the changing resin formulas. For the most part, with a carbon steel tank, you know what you're getting for steel. On the fiberglass side, it's a little harder to tell exactly what resin formula they're using and what impact that'll have long term. But obviously, you don't need things like cathodic protection like you would on a steel tank. Um,
Adding in one other, Alex, just you don't see them too often, but you also have your other fluids that you may be designing around as well. Depth, for instance, right
oh,
now is huge.
yeah,
And the entire depth system must be stainless steel. Otherwise, you'll get a lot of corrosion. So your main tank is stainless steel, your piping, your pumps, and everything is stainless steel. And nowadays, with the environmental concerns, just like they started adding depth to all of your trucks that are out there on the road, you have them for generators also. So that's another very large system that you need to be cognizant in how you design it and what materials that you use.
absolutely. Yeah, we're seeing, although we're not seeing it implemented yet in a lot of places here, it's definitely on the horizon. The diesel exhaust fluid portion of that, and you're right that that has to have special material consideration throughout. For the steel, what about seals? What are you seeing on DEF for seal material?
Tell you the truth, I wouldn't be the expert on that, but yeah, I can tell you everything is stainless steel. As far as seals between, much of it is welded, to be honest with you, as far as seals on
Yep.
different areas, but anything that is flanged, I'm not really sure, to be honest with you, Alex, what they're using in between.
Well, I'm just thinking like for transfer pumps, we have transfer pumps that are rated for DEF.
Yes, we do. We do. And I'd have to look up what the actual seals would be.
Okay, yeah, excellent. All right, so tank location. So again, talking about what is the physical construction, physical placement of these systems, right? Does it matter? And as we mentioned before, as far as thermal cycling, right, that can be a big impact. One of the things that I always think of is, if you're above ground versus below ground, it can definitely affect your calculations on your transfer pumps. Below ground tanks, you definitely want to reach out and either have those calculations for pump sizing on the suction side, or reach out to us and let us walk you through that. As far as construction down where you are, Brent, when you're looking at an above ground or a vaulted tank, when I say vaulted, I mean not direct buried. It's in like either a basement in the building envelope, or it's in its own separate, concrete vault outside. Other than the vapor monitoring, is the construction of the tank fairly similar? Because we would do almost exactly the same type of construction for above ground as we would vaulted.
Exactly the same, really. And all they do is have a concrete vault around it that you can usually enter in some way, whether it's opening up some uh, doors or, so in basements, for instance, if the building is just being built, you will find tanks in basements just to conserve space. They put them down in the lowest, area of the building. But those are just above ground tanks that are surrounded by concrete, more or less.
Right. And so we touched on it a little bit earlier, the different types of steel tanks that you're going to run into. But I would say for us, it would start at UL 142, right? That'd be kind of the basis for a double wall steel tank. And then the top end would be the UL 2085 fire guard with the interstitial porous concrete, with the ballistics rating, the fire rating. And then in between, and it's kind of lesser known, but it's been very helpful to kind of have in the back pocket when you have applications where whether the fire department or the insurer wants something more than UL 142, but the project may not support literally may not support the weight of the UL 2085, or the cost would be like a STI Steel Tank Institute Fire Guard tank, or sorry, Flame Shield rather. The UL 2085 would be the Fire Guard. The STI Flame Shield, which is very similar to UL 142 construction, but has some certifications and a 30-year warranty. Do you see that where you are as well?
I have. I've run into it a couple different places. There are a lot of generators. Let's just say this: the more fragile that our power becomes, the more folks are looking to add in, especially life safety type generators. These could be for an existing apartment complex that was built, you know, 50 years ago, or an old courthouse building that, may be 50 years or more uh, old. They can't sustain the weight of a generator on the roof.
Mm,
So architects really have to put some thought into how much weight they have, not just for the static material, but also filling that tank with fuel oil. So there are restrictions there. It could be the size of the tank may be reduced. Your runtime may be reduced. You may opt to do a tank in a vault or underground if you can nearby that's pumping and pushing fuel up to areas. Recently, we've even had some inquiries about designing large mission critical data center projects that are 3 or 4 stories tall that may house 50 plus generators. And you have to imagine the weight of that building and each floor of that building when you have that many generators just stacked on top of each other. Not to mention, because they are mission critical, many of those belly tanks that are being supplied with the generators could be upwards of 5,000 gallons apiece. So that's
right.
a tremendous amount of weight, and that's where you start seeing like the flame shield tank or something that is not UL 2085 because of the added weight to that. Um, but as we develop, and I'll say this, the more that the government went to environmental concerns with and attempt to add additional um, environmentally safe power, which would be air turbines or wind turbines or solar or those types of things. Right now, fuel oil is still the primary backup of all of those systems. So the
Mm,
more of a push to go green, um, we've seen a pretty steep influx of fuel system projects and backup power systems.
right. Yeah, and one of the things I just take very briefly as an aside to encourage people, as these systems get larger, one of the things that we have learned along the way, it's not enough to just take a regular system design or the way things have been designed before and just multiply everything times two or times three. As systems get larger, as they get more complex, you're going to want somebody who's familiar with how to handle the controls and how to handle those higher flow rates and pressures. Reach out to us, reach out to a fuel oil expert, and work with them on these projects, because as they get larger, the potential for spills, the potential for environmental impacts, all of that goes up. And so, all right, so talking about tank locations, we talked about underground versus above ground a little bit already. Things you got to look out for. Do you need impact protection? Is there need to be UV protection if you're above ground? How are you going to inspect the tank, right? Is it in a vault where it's a confined space, or is it something that's easily inspected? I get a lot of questions where maybe it's in a basement and they want to put it against one or more walls. How close can it be to the wall, right? So these are all things that you want to kind of look at on a case by case basis. And then we're talking about the physical construction, right? It's not just the material the tank's made out of, but it's the coatings. Now, on the outside of most steel tanks, it's going to be pretty similar. It's just going to be standard UV or corrosion protection. If you're in a maritime environment, that might change a bit. One of the things that Brent alluded to earlier was a hybrid when it comes to underground tanks that we've done in the past, where it's steel inner with an FRP clad outer. Um, One of the advantages here is that you're working with a steel tank, but it's very, very well protected against corrosion. So it gives you a little better footprint there. And most importantly, when we talk about footprint, I think a lot of people, they get the idea that it's the actual space it occupies, right? When I'm talking about footprint, one of the most important things is not the total space that an underground tank occupies, it's also the depth. If you have an area where it's not just out on a lawn, where it's maybe in a parking lot or anywhere where a truck can, run over it, and you're looking at, say, H ratings or things like that, the footprint, what we're really talking about here is how close to the surface can that tank be? Because for every foot you push that tank below the surface, whether it's for a concrete cover of some kind, or whether it's just depth below the surface, so you need a certain amount of fill, that's going to impact the performance of your fuel system, right? Because that's another foot that you have to lift the fuel out of the tank by the transfer pumps. So that can actually have a surprisingly large impact on the performance of the system. And then lastly, we talk about tank lining. This is something that we don't see on every project, but if we had a project where it's life safety, mission critical, we're looking to go belts and suspenders. As we talked about before, the interior of the tank, you get these areas of welds in different areas where you can start getting some pitting and sludge formation that can become a vicious cycle where the acidic byproduct can then continue to attack the steel or attack the resin on the inside of the tank. So one of the options there is to go ahead and do an inert coating. And again, this will be dependent on the application, but there's whatever the application is, there are a lot of options out there. The important thing with main tanks is there's no one size fits all. There's really no standard size or form factor. It's whatever the job needs and whatever the job can support.
Yeah,
So
I'm seeing a lot of that, Alex. There's a lot of older tanks out there. Some of them, when you start thinking about sizes of tanks in general, usually you find that they're limited to about 50,000 gallons, especially underground. And that's because that's about the largest that you can easily transport without field erecting or field mending parts of the tank together in the field. And but that being said, there are a lot of uh, literal single wall tanks that are in the ground for a lot of older facilities, especially military posts, where that lining has been the I'll call it the poor man's response to environmental concerns or sludge buildup over the years, like Alex mentioned, where you're beginning to pit and weaken the metal. And what they're doing is instead of ripping those tanks out of the ground, they are reusing them, bringing them new life by putting in linings and spray in linings that protect that fuel and may give them another 20 years of those tanks. So that's just something else that we've seen around the area.
yeah, and in fact, I've seen, now that you mention it, I've seen that also on biofuel applications where it would have been an application that would have called for a stainless tank, but there were some existing carbon steel tanks, and one of the options was to do an interior coating that was
Absolutely.
or compatible. And so, saved the hundreds of thousands of dollars it would have cost to build new stainless tanks by retrofitting the existing. So, yeah, just another case where reach out and ask some questions. You may find some options that you hadn't thought of. And again, encouraging everybody when it comes to these systems, especially as they're getting larger with biofuels and other impacts like that, please reach out, give us a call, um, or send us an email. We'd be happy to take a look at any project that you have or just answer questions. Brent, I don't know about you, but I find that some of the questions that I've never heard before can be really interesting, and it's fun to see the different applications that people have around the country.
Oh, it is. It is, Alex. I mean, I love what I do, and I've been doing it a long time, but nothing surprises me anymore. I still get a lot of, calls for not just standard equipment, but all of these like I said, everything's getting larger. Everybody wants to do larger systems. How much can I do? How much fuel can I hold? What materials do I need to use? And think about the future, or in this case, hey, DEF or whatever it may be. There's always something new, and if if we can't answer the question, we will certainly help find an answer to the question, however that may be. We have a tremendous amount of support from our home office, our factory office. We have dozens of engineers that have been with the company, for many years apiece, and we can rely on that. We can reach out to other contacts and see who has run into something similar. Uh, there's no wrong question. And if there's a way to do it, we, as an engineering based manufacturer, can certainly help do it.
Absolutely. And we have that deep bench. We want to make that knowledge and that experience available to you. And we have contacts in the industry. Maybe it's a tank that we don't make, but we work with tank manufacturers, leak detection companies, all of this. So if it's anything related to that, feel free to reach out to us, and we're more than happy to get back to you any way that we can. Thank you for your time watching. We really do appreciate it. Please send in those questions, whether it's questions following up via phone or email, or you're on the chat right now. And I think we're going to try and go ahead and answer some of these here in the next few minutes. All right.
Great. Thanks, everyone.
Okay, well, thank you for everyone who was able to attend the webinar. We definitely appreciate your time. We have several questions here in the inbox that I want to go over if you have a few minutes to stick with us. First one is, how often do we see submersible pumps on fuel oil transfer systems to day tanks? I probably run into every couple of years a design or a system where we have submersible pumps. Uh, it really depends. We are the standard basis of design that we typically do are going to be are certainly going to be not submersible. They're going to be self-priming. Depending on the application, whether it's a spur gear pump or something along those lines. But we still run into them, and it's usually on applications where, for some reason, we can't locate the transfer pumps close enough to the tank to prime. There's some sort of space constraint, uh, at least here in the Northeast. But keeping in mind what the limitations there are, when you have submersible pumps, you tend to have a higher flow rate for the same horsepower, but you're really limited on discharge pressure. So if it's an application where there's a lot of head pressure, maybe it's a tall building, you may be really limited on that, and the pump curve is going to be quite pronounced too, as opposed to a positive displacement pump. So we don't see them that often, but we do run into them, and we sometimes will need to control those pumps in our systems. Brent, what are you seeing down there in your territory as far as submersibles?
Well, I'd say they're starting to become about 50-50, and I'll explain
Wow.
why. Yeah, I've seen a lot of projects now relying on submersible pumps. And the reason for it is these large 50,000-gallon underground tanks. Obviously, location is a huge consideration. When we are using a positive displacement pump skid, we have to do the math, and we have to do the pipe sizing and depth, and the amount of fuel that we're moving are all key considerations. Submersible pumps are great at flowing a large quantity of fuel. However, they aren't so great when it comes to head pressure. So if you're trying to pump fuel to a second, third, fourth floor somewhere like that, or a long distance, and you're losing a lot of pressure from the pipe sizing that you've gone with, submersibles may not be the best idea. Positive displacement, you can do hundreds of gallons of per hour or per minute flow rates at very high pressures. Recently designed a couple projects where we needed about 200 psi, and that's something that a submersible pump won't do for you. However, the downside is when you get into these underground tanks that may be, might have 4 feet of overburden plus a 10 or 12-foot diameter tank underground. Where do you put that pump skid?
Hmm.
Some of these tanks are out in a parking lot, and the nearest location for a pump skid may be hundreds of feet away. So not only are you pulling a horizontal of hundreds of feet, but at the same time, you've got to pull fuel up upwards of 15 or 20 feet, which is about the maximum of a submersible or a positive displacement pump skid. So
Right.
there's considerations both ways.
Absolutely.
Other, yeah, and Alex, the other thing that we run into, we've spoken a lot about fuel filtration, and when you try to filter fuel, and sometimes this is sort of your uh, you run out of options with submersible pumps and filters.
Hmm.
Positive displacement pumps can filter fuel a lot easier. They have an open drop tube that is pulling fuel through a strainer basket that is relatively your pre-filter before pushing it through the filter unit. whereas a submersible pump actually has a screen on it. And if you're using the same submersible pump as you are for your uh, filling your day tanks, that particular stem of that submersible pump is only going to go down into the tank so far. It may not be getting the water off of the bottom. And also, sludge buildup can really clog the intake of a submersible pump as opposed to a positive displacement that has a strainer. So these are all considerations, but um, for the most part down here recently, the many of the larger projects that have a ton of bulk storage, 4, 5, 50,000 gallon underground submersible tanks, underground tanks, have been supplied with very large submersible pumps that can flow a tremendous amount of fuel.
Hmm. Interesting. And I think one of the things we want to make sure to clarify right now for anybody that's listening, because there is a bit of a place where we can trip up on terminology. When we're talking about submersible pumps, I think most people understand that we're talking about a pump that's actually down inside the fuel tank, right? One of the things
Mhm.
that we have done a lot of are waterproof pumps. And so sometimes we get questions for submersible and waterproof. We kind of get the lines crossed on those. The waterproof pumps that we offer are fully enclosed and it can be submerged in water, but they are actually a positive displacement pump, just like we would use on a typical application. So just wanted to make sure we are clear on that point there in case there's any confusion in terminology.
Yeah, the
Um,
waterproof pumps have been great for flood prone areas. Even if they're only at risk of 100-year flood, we use those in totally enclosed waterproof positive displacement pumps that give you all the benefits of positive displacement, but also are protected from water intrusion or in flood zones. And I think, Alex, we've tested them down to about 40 feet underwater without issue. So
we did an
that's an
equivalent
option.
test at the factory to, I believe it was 5 or 6 stories underground.
Oh,
That
wow.
I observed back years ago. Yeah, for a healthcare application in Boston. Um, and it's interesting, some of the side benefits that we see on a product like that. One of them, was being mentioned to me by a customer, things like impact protection, the fact that they're fully enclosed. If you have a leak on one of the pumps, it contains it. So we've seen some side benefits as well of that application. Another question we have here, reasons for vaulted tanks. Up in the Northeast, usually tanks, I mean, if you're talking about a vaulted tank, a lot of times you're talking about a tank in a basement, right? So a vaulted tank could just be any tank that's above ground, but inside the building envelope. Whether or not it's a vault per se, might get into some more specifics as far as the job. Reasons for that, I mean, containment, real estate space. What about you, Brent? What are you seeing down there?
So the time that we're seeing the vaults are when you want to use, say, a positive displacement pump or have a filter unit or have additional equipment in the same room, and you don't really have a room in the building to put this equipment in. You can do a vault design that has access where your pump skid, your filter unit, uh, and anything else that you needed close in near proximity to the tank can all be placed in the same room. The other thing that we're seeing is when they are required, it's typically because you have a lack of fireproofing available. So underground tanks are inherently fire resistant because you're not typically
Hmm.
going to see a fire go underground, right?
Right, direct
Um,
buried. Yeah, the exposure is
direct
limited.
buried. Right. Some of the tanks that are in basements, for instance, and they're required to be in a fire resistant room, usually between 2 and 4 hours. So having a vaulted area can actually protect you from fire as well. If you want that package and that tank and whatever equipment in a separate location outside of a building or underground in a building, but again, be accessible for you to be able to monitor or maintain in some way, for maintenance purposes.
Excellent. All right. Well, I think that just about does it. That is what we had for questions there in the chat inbox. Please email us, give us a call, send us a text message if you'd like. Our contact information is there on the screen. And I believe that we will be posting in the near future a recorded version of this on our YouTube channel as well. Thank you again to everybody who participated. Thank you for the questions. Thank you for your time. And we look forward to talking to you again soon.
Alex, it looks like we might have one more come in. Let's see here. Submersible pumps are similar to what one would use for filling
Yeah, I think
stations.
that
Yes,
was a
they
follow-up
are.
on the previous one. Yep.
Yeah, they are. So typical gas stations all use submersible pumps.
Right. Okay. Thanks, everyone.
Reach out if you have any questions regarding any of what we've covered today or anything fuel oil related. We're happy to help.